In today's lesson, we're actually going to be looking at a method that allows us to generate estimators. So over the past few lessons, we had looked at sampling distributions, which talk about the distribution of an estimator. We had looked at the sample mean specifically and saw its sampling distribution. And then we talked specifically about point estimation, and we talked about how estimators are random variables and they produce estimates. And these estimates are going to be single values, and we want them to be close. And we can sort of measure how close they are to the truth using the MSE. And the MSE is given by the square deviation, taking the expected value of the square deviation from our estimator to the truth. Right? And this is going to be composed of both the bias, which is how far our estimator is in expectation from the truth, as well as its variance, which we've seen variance a whole lot throughout the term. Right? And so we sort of have this framework where once we sort of have an estimator, we can start thinking about what's its distribution, how does it behave, is it a good estimator? But what we do not have yet is sort of a method for determining estimators. Right? We've seen estimators for the case of the sample mean, for instance, or for the mean using the sample mean, but we don't have a reliable way to generate estimators, right? So if I were to give you a new distribution and say, how would you come up with an estimator for a parameter from this distribution? We don't yet have a way of doing that. And so in today's lesson, we're going to talk about one of these techniques, and it's going to be known as the method of moments technique. So with the lesson today, we mostly just want to understand what is the method of moments technique? How do we use it as an estimation procedure? Right? And so to motivate this discussion, I'm looking at a picture here, which is some sort of maze, right? And I guess the thought process here is that estimation procedures essentially allow us a determined way to be able to come up with point estimates that are going to be at least, somewhat well behaved, right? No matter what it is in the population that we're trying to estimate, the idea is that following these procedures is going to allow us to get to an answer, and this answer might not be the best possible answer, but it's going to be one that we know something about and that's reliable, right? And so it's the same idea when we're trying to, say, solve a maze, right? You want some sort of strategic way of searching your way through the maze, right? So that no matter what maze pattern is presented to you, you can always find your way to the exit. And so that's the sort of idea there. Now, once we have an estimator, it's going to be easy to generate estimates, right? The estimator is just a function. And if I were to give you a function, I'm sure all of you could take a sample of data and compute the actual estimates from that. Now, sometimes there are very obvious candidates for generating estimators, right? So if you want the population mean, then it's pretty obvious to think about using the sample mean. Same thing with the population variance, sample variance. But other times it's not going to be so obvious about how we might consider generating an estimator for different population values, right? And so in those cases, this is where estimation procedures are quite important. Estimation techniques, generally speaking, are designed that in such a way to allow us to generate estimators for parameters of interest in a very general setting. So they're not specific to the mean or the variance or any other specific property. They give us a recipe that we can follow no matter what it is that we're trying to estimate. There are really two major forms of estimation techniques, or at least two broad forms that occupy sort of a large category of the estimators that you could possibly see. The first one is maximum likelihood estimation. Now, this is sort of a very theoretically rigorous way of estimating parameters. It is definitely the most prominent estimation technique. The textbook addresses it a little bit. We're not actually going to cover it in this course. And there's some drawbacks to using maximum likelihood estimation. But if you were to take on further stats courses, MLEs or maximum likelihood estimates are probably where you'll focus. In this course, we're going to look at methods of moments. Now, the method of moments is an intuitive technique, and it's typically going to generate robust estimators. So we don't have to make strong assumptions about the underlying data in order for these estimators to be good. On the flip side, they're not normally going to be the very best that we can do. So it's gives us sort of an easy process to follow to generate these estimators. They're not going to be perfect, but normally they're going to work well enough for our purposes. So how do we actually start thinking about the method of moments? The idea first is that we have to define what we mean by a moment. So we've seen that the expected value of a random variable is denoted e of x, right? We can also call this the first moment. Now, if you consider e of x squared, that's what we would call the second moment. And so we know e of x squared is related to the variance, but it's not exactly the variance, right? And so we know how to compute the expectation of a function of a random variable. And so we can just compute e of x squared like this. And we give this special name, the second moment. Now, in general, if we take the expected value of x to the power k, we're going to call that the kth population moment, right? If you've taken some physics courses and maybe in some of the engineering courses, you may have seen moments in other contexts. They're actually exactly the same thing here. But generally speaking, in stats, all that we care about is that the kth moment is going to be the expected value of x to the power of k. Now, generally speaking, these moments, the population moments, are going to be functions of the unknown parameters of the distribution, right? So no matter what distribution we have, it's going to be parameterized by some unknown parameters, and the moments are going to be functions of those. And we'll denote all of the parameters that we're trying to estimate as theta. So sometimes that might be a single parameter, just mu. Other times that might be sort of a set of two parameters, say mu and sigma. And other times you might have sort of a long list of parameters that define a distribution. Sort of no matter what, the moments, the population moments, are going to be functions of theta. Now, if we had a sample of size n, then we could also consider the sample moments, right? And there's sort of a natural way of estimating these. So the first sample moment is the sample mean. We've seen this a bunch, right? And it's sort of the sample equivalent to taking the expected value of x. If we wanted to generalize this in the same type of way, then we could just take the sample mean of x to the power of k, right? So if you square everything and take the sample average there, then you'd get the second sample moment. And so we'll use this m hat sub k to denote the kth sample moment. And again, generally speaking, once we have a sample, these are going to be easy to compute, right? So these are estimators, but if we were given a sample, we could actually estimate all of the different values here. Once we have all of our sample estimates, we can sort of map them onto those population moments, right? So if you know the first sample moment is some value and the first population moment takes on some form, if you set those equal to each other, then that sort of gives us a mapping of what these things should actually be. And that's the intuition behind the method of moments. So to put it concretely, if we have L parameters that we want to estimate, so remember we're estimating theta, but theta might be composed of the mean and the variance and perhaps some other parameters that define the range or whatever else. So we're going to say that there's L of them in total. The first thing that we're going to do is compute the first L population moments. Okay, so that's going to be the expected value of x, the expected value of x squared, and so on up to the expected value of x to the power of L. And we're going to express these all in terms of functions of theta. The idea is that we want L different unique functions of theta. Okay. Once we've computed the L population moments, we're going to compute the first L sample moments. And because we have some sample, these are all going to be computable on that sample. And then we're just going to set m hat k equal to the expected value of x to the k for all of the k from 1 to L. This gives us sort of a system of equations, right? There's going to be L equations, we have L unknowns, and so assuming that this system of equations is actually solvable, we can then solve for the parameters theta. And when we solve for those parameters theta, that's going to give us an estimator, or if we're working from a specific sample, that's going to give us the estimates themselves. right? And so that's the idea with the sample or with the method of moments. So we set the population moments equal to the sample moments and then solve for the estimators from there. Now, generally, these estimators are going to end up being robust, right? We haven't made any assumptions about the underlying distribution, or at least not very many assumptions about the underlying distribution. And so they're going to be fairly robust. They're going to be quite intuitive. And we're going to find that they're comparatively easy to compute, right? It's not always going to be easy to find the population moments, but if you can write down the population moments, then of course, getting the actual estimates are going to be quite straightforward. And I'm sure you're all familiar with actually solving systems of equations, right? And so sometimes they can be difficult, but typically they're more tedious than they are conceptually challenging. Now, one thing that we're assuming here, and it's a point that we're happy to assume throughout this course, but I do just want to draw attention to, is that we've made the assumption that all of the population moments actually exist. There's going to be distributions, and this may sound weird, but that don't have an expected value, or that don't have an expected value of x squared or of x to the k, right? And the idea there is that the integrals that define these expectations might not actually be convergent integrals. And if they're not, then of course we can't use the method of moments here because we need to be able to write down functions for those, right? So we're assuming that they exist. They're going to exist for all the distributions we care about, but it is worth keeping that in the back of your head as to a shortcoming for the method of moments. It's also going to be the case that generally method of moments estimators are biased, right? Which we talked about in the previous lecture, that biased estimators are not generally preferred, but sometimes it's going to be okay to use biased estimators, right? And so as a general rule, the method of moments are not going to be unbiased estimators of the truth. Now, the last point here is that the method of moments estimators do not need to be valid parameter values. And what do I mean by this? Well, if you think about something like the variance, right? We know that the variance has to be greater than 0, right? And the way that we compute the sample variance, generally speaking, is going to be the case that we're always going to get something that's greater than or equal to 0, right? And so there's sort of this range of valid parameter values, and an estimator, we hope, preserves that range of parameter values. It's not generally going to be the case that in method of moments estimators this happens. It's going to typically be possible for you to estimate a value for a parameter that's outside of the possible values. And if you ever do that, then what you should do is just take sort of the maximum or the minimum allowable value as your estimate instead, right? So if you were to estimate a variance that's a negative, for example, then you would end up just taking your variance to be sort of some very small positive value, right? So that's another sort of shortcoming there. We have on one hand that they're robust, easy to compute, and fairly intuitive. On the other hand, they won't always exist. They're typically going to be biased, and they might not produce valid estimates. So, to summarize, estimation techniques are going to be general purpose processes to generate estimators. The method of moment is one of these techniques, and the way it works is by taking the population moments, setting them equal to the sample moments, and solving that system of equations. The method of moments are typically robust and intuitive, but they're generally going to be biased and they may not exist. So I hope that most of this made sense. I'd encourage you all to sort of start exploring the method of moments sort of hands-on and getting a sense for how those all work. And I hope to see you all in the next lesson.